notes are about a number system called complex numbers. Why do we need this new number system? Aren't we just happy with the real numbers that we have? Well, take a look at this blue equation. X squared equals -9. If you try to solve that, we know that we would try to square root each side, and we would get that x equals the positive or negative square root of -9. What number times itself gives you -9? You probably can't think of any such number if you're only thinking about real numbers. So we've created this need for a new number system where we can have square roots of negatives. And we have this set of numbers called imaginary numbers. And what they represent is square roots of negatives. So now I can have some sort of meaning to the square root of -9. But we do have some notation that we have to introduce first. Imaginary numbers are based on one definition, and that is that we call this letter I, it's a lowercase I, and we assign that to mean the square root of -1. It's just a definition, but it allows us to help write square roots of negatives in terms of I. Here's what I mean. Let's look at the square root of -9. I can break that apart, by definition, into root -1 times root +9. It's kind of a definition of how we would generate these imaginary numbers. Root -1, we have a special name for. We would call that I. Root 9, we know what that is, and that is the number 3. I usually has the place in an expression like where an x or a variable would. So we would never call that I 3. We would call that 3I. That's how we can simplify or write in terms of I this square root of -9. So now all the way back here up at the top, I can actually have a better answer here. X equals plus or minus 3I. Let's try some more simplification. How about this one? Square root of -7. I know I can break that apart into the square root of -1 times the square root of 7, and that would give us I root 7. Root 7, we can't really simplify any further. On the previous page we had root 9, which we could call 3, but here root 7 is just going to stay root 7. And this is how we would write root -7. We would call that I root 7. Notice the I is out front of the radical. We would not call that root 7I, because then it might accidentally look like the I is underneath the radical bar, and we want to make sure that it's not, so we write it out front. Here's one more. How about root -16? Well, I know that that's root -1 times root 16. Root -1 I know has that special name I, and root 16 is of course 4. So we would call that 4I. Notice some square roots of negatives, if we have a perfect square under the radical as well, we can completely simplify. We just call that 4I in this case. But in the example above it, sometimes we can't simplify that radical, and you're left with something just like I root 7, I root 13, whatever it may be. Once we talk about these imaginary numbers, which is the types of numbers that we've just talked about, we can now talk about this set called complex numbers, which are numbers that involve both a real part and an imaginary part. They are in the form A plus BI. The BI part, that's kind of what we just talked about, like I root 7 or 4I. That's the imaginary part. The A, that's just representing some sort of real part. And a real number, of course, that's everything that you're used to. So here's an example of a complex number. Something like, I don't know, 2 plus 3I is complex. It has a real part and an imaginary part. And we'll see how these numbers show up in solving equations. Let's see. Let's try to solve the quantity x plus 3 squared plus 13 equals 0. Notice what this is. It's a quadratic equation. Our quadratic function happens to be written in vertex form and set equal to 0, so I know we can do this. We've seen equations like this before. Well, we could subtract 13 from each side, and we get x plus 3, the quantity squared, equals -13 Now we can square root both sides, remembering we need a positive and negative square root. And notice back before we talked about complex numbers, we would stop here and say, oh, there's no real solution because we have the square root of a negative. But we can go a little further now that we know how to write complex numbers. I can call this plus or minus I root 13 by writing it in terms of I. I didn't go through that step like I did before of calling it root negative 1 times root 13, because you should get used to that fairly quickly. Now we only have one more step. We can subtract 3 from each side. And we get that x equals negative 3 plus or minus I root 13. Now I do have actually two answers that I can talk about. X equals negative 3 plus I root 13, and x equals negative 3 minus I root 13. Now I know a couple things about my solution here. I know that it is a complex solution. It does have an imaginary part. So if I'm thinking about where this function would cross the x-axis, I know that it has no x-intercepts. There's no real solution, meaning that that function has no x-intercepts. But I can talk about a complex solution just to this equation. It doesn't really mean anything for us right now graphically in terms of the graph of that quadratic, but I can talk about a solution now. I can have a complex solution to that equation. Now we're going to talk about some operations on complex numbers. First we'll try adding two complex numbers. Let's try 2 plus 3i plus 5 minus 8i. Two complex numbers, and we're adding them together. How might you think you would add these complex numbers? It's probably what you want to do. You would just add the real parts. So 2 plus 5 is 7. And then you would add the imaginary parts. 3i plus negative 8i is negative 5i. Just like expressions involving x, 3x plus negative 8x is negative 5x. Same thing here. And that's it. So this is just 7 minus 5i is that final simplification. You add the corresponding parts. How about subtraction? Let's stick with the same two complex numbers and see what we get when we subtract them. 2 plus 3i minus 5 minus 8i. Well, addition is just like, subtracting, is just like adding negative numbers. So it really is the same thing. You're going to subtract the real parts. 2 minus 5 is negative 3. And then subtract the imaginary parts. But be very, very careful. 3i minus negative 8i is really 3i plus 8i. So we get plus 11i here. This is where subtraction might trip you up. If you were subtracting a negative, we have to remember that we're really adding. One more operation to talk about today, and that is multiplying. Before we go through multiplying two complex numbers, let's talk about a special property of this I thing. I want to figure out, what is I squared? Well, I know that I squared is I times I. And I know that I represents the square root of negative 1. So that's the same as saying the square root of negative 1 times the square root of negative 1. And by definition, multiplying two square roots that are the same will just generate what was underneath that square root. So we can treat this almost like a definition, that I squared is equal to negative 1. That's really important because this is the first number we've ever seen where we can square it and get a negative. And that's exactly why we've decided to use these to represent our solutions when we have square roots and negatives. So the other way works too. I squared is equal to negative 1. That's going to become very important when we look at how we multiply two complex numbers. Let's stick with those two complex numbers we had from the previous examples, but this time we are multiplying them. You would multiply them just as you would any other two binomials, like, 3x plus 5 times 4x minus 1, something like that. You would sort of do all those distributions. So 2 times 5 is 10. 2 times negative 8i is negative 16i. 3i times 5 is 15i. Notice I is almost acting just like an x or something like that when we multiply. Our last term here is 3i times negative 8i, which is negative 24i squared. The I squared showed up. That's why we talked about this definition up here. It's going to become very important. Notice we can simplify like terms. Negative 16i plus 15i is negative 1i. And then the I squared is negative 1. So I'm going to replace this with a negative 1. So 24i squared became 24 times negative 1. Notice we had a minus 24i squared. So minus 24 times negative 1 is going to become a plus 24. Let me just write in those other terms. So our final answer, well, our answer is coming down to 10 minus I plus 24, but now we can combine the 10 and the 24, and we get 34 minus I. So notice what happened. That I squared term ended up being able to combine with our real part out front, and that will always happen if you have an I squared term, so don't forget about that. You might be wondering if we're going to talk about dividing complex numbers, and we're actually not for now. We might do that a little bit later. But for the purpose of this video, I wanted to introduce you to what complex numbers are, how we see them when we solve equations that before we had thought just had no solution, but it turns out they do. There's just no real solution. How we would add them, how we would subtract them, and how we would multiply them. So good luck practicing.